Okay, Module 7 time, and one thing I want to, first of all, allay your fears. This is a lot of material. You know, this module is going to cover 3 chapters, chapters 8, 9, and 10. We've actually, in previous modules, only covered 1 chapter or even parts of a chapter. So this is going to seem like a lot of material, and it is. In fact, this material, and if we extend it into, say, chapter 11 and 12, that often is actually a course unto itself. In some colleges, they actually have a course about comparative planetology, where you're studying just the planets of the solar system and comparing their compositions, their atmospheres, magnetic fields. We're not going to get into all those minor details. And so we're going to actually move through the solar system relatively quickly. So between this module and the next module, we're going to blow through the entire solar system. So I'm not going to focus on the minutia too much. What I want you to really focus on in this module is, first of all, what the solar nebula hypothesis is. You know, it is the leading idea as to how the solar system came to be. It's important that you understand that, because from that, we are going to see some of the basic differences between the different planets. We're not going to get focused on the minutia, but it is important that you understand why there are differences between what are called the inner planets, or the terrestrial planets, and the outer planets, which are also called the Jovian planets. It's very important for you to understand that, and that actually is a direct consequence of the solar nebula hypothesis. So those are some of the fundamental things you really want to be looking for in this module. Don't get too hung up on the number of moons of a particular planet and all that kind of stuff. But you know, and naming certain features on the surface of a planet, that's not as important as the big picture. Why, first of all, the solar system came to be in the first place, and the evidence that supports the solar nebula hypothesis. One of the first topics you're going to hit here in Chapter 8 is the solar nebula theory. And I wanted to tear that apart first of all. You know, solar, what does that mean? In this case, it means, you know, solar usually means sun. In this case, it's the sun and the planets, what's called the solar system. Nebula, if you've ever heard the term nebulous, it often if someone is referred to as having nebulous thinking or nebulous explanation, it kind of means foggy or hazy. And that's actually because it comes from a Latin root for cloud. And now the term theory. Theory in our common way of speaking is quite often just kind of dismissed as, oh, it's a guess. But in science, a theory has an entirely different meaning. A theory is essentially an explanatory framework that explains a bunch of observed facts. So, for example, as we're going to learn later on in this chapter, all the planets orbit the sun in the same direction, in a counterclockwise view when viewed from above. You know, that's a fact. Now, how would you explain that? Well, you explain it by the solar nebula theory. So a theory in science is, like I said, an explanatory framework. It explains away a lot of facts and observations, data. Now, the solar nebula theory essentially is what you see on the screen here. The idea that the sun and the planets, our solar system, essentially arose from a cloud of gas and dust in space that started to rotate about 5 billion years ago, contracted into the current objects, the sun, the planets, and as we're going to learn, comets, asteroids, etc., etc. That's the idea. That's the theory. Now, this theory has been around for several hundred years, and there's been, you know, it is the leading theory. There are other explanations as to how the solar system came to be, but this one is the one that has the most support. Sometimes people ask, well, do you believe in this theory? I don't buy the term believe. It's what do I have confidence in? I don't really like the term belief. I like the term, or the idea, what do I have confidence in? And the theory that has the most confidence at this point in history is the solar nebula theory. It has the most evidence that backs it up. Now, a good theory not only should have explanatory power, but the best theories have predictive power, meaning that not only do they explain what we're seeing in our own neck of the woods, but if this is the way solar systems come to be, we should be able to see this in around other stars, because our sun is just one star among billions of other stars. If this is how our solar system came to be, shouldn't the same thing be happening in other solar systems or around other stars? And it turns out this is only a development of the recent decades. Only within recent decades do we have the technology that allows us to peer into other stars and see stars and solar systems forming. And that's the cool thing. Even though this theory has been around for hundreds of years, its true predictive power has not been able to be tested until more recently. And all of our tests, all of our observations for what are called extrasolar planets are indeed confirming the solar nebula theory, that this didn't just happen for our solar system, but indeed other solar systems are forming in similar ways, which again is more evidence, more confidence in the solar nebula theory. Again, a theory, as I'm trying to impress upon you, is not just a wild guess. We have a thing called the germ theory of disease. If you have an egg salad sandwich sitting out on a park bench all day and you decide, okay, I'm going to eat it, it's going to make you sick. Well, why is that? Well, one explanation could be that there's a demon inside you that does not like egg salad and wants to get rid of it. But that's not really a good explanation, and it wouldn't predict that other people would get sick from the same if they ingested the same spoiled sandwich, because that would mean they would have to have demons inside them as well, and everyone had that doesn't make a whole lot of sense. A better explanation, an explanation you can have more confidence in, is the fact that there is bacteria that grow on that egg salad sandwich, especially on a warm day, microbes that when ingested into your body reacts to and tries to get rid of them. And that would explain not only why you got sick, but it would also predict that if some other joker walked along and ate that same sandwich, they would have a similar reaction. So that's essentially the solar nebula theory. And like I said, in science, a theory has both explanatory and predictive power, which indeed the solar nebula theory does. This is an image from page 146 of your book, mainly just to give you an idea as to the relative sizes of the different objects in the solar system, including the sun and the planets. And one thing that you should notice is that they're not all the same size. All the objects are vastly different in size. And the solar nebula hypothesis, or the solar nebula theory, should be able to explain the differences in the relative sizes. And that's something you should be keeping a close eye out for as you're reading is, how does the solar nebula theory explain the variations in the sizes of the planets? Okay, so these are the planetary orbits, essentially to scale in the solar system. And one thing you should notice is that all the planets are orbiting in the same direction, essentially counterclockwise when viewed from above. That's relatively interesting, and again, that is a piece of evidence that increases the confidence in the solar nebula theory. The solar nebula theory would indicate that if all the planets form from a rotating cloud of gas and dust, that cloud would have a certain sense of rotation, and that rotation should be demonstrated in the orbits of the planets. Another thing you'll notice is that the individual planets rotate in the same direction, with the exception, there's a couple of exceptions. And so that not only is consistent with the solar nebula hypothesis and actually gives evidence, but the fact that some of them don't, there's got to be an explanation then for that, what would appear to be an exception. Another piece of evidence that's very interesting is the fact that all of the planets essentially orbit the sun on a plane, and that plane is the ecliptic. And so they're all essentially on the same plane with, again, a couple of exceptions. And so not only does that commonality provide a little more evidence for the solar nebula theory, but there's got to then be also an explanation for the exceptions in order to keep the solar nebula hypothesis as the leading hypothesis. I'm not a big fan of memorization in science, but you should at this point have your planets memorized from closest to the sun to farthest from the sun. And when you do that, you'll notice that there are two groups that we can, once we have those 8 planets kind of memorized, we can actually group them into inner planets and outer planets. The 4 that are closest to the sun are called the inner planets, or sometimes called the terrestrial planets, and the ones that are farther from the sun, those are considered to be the outer planets, or the Jovian planets. And as we're going to find out, the reason why we can characterize them is because those 2 different groups have vastly different characteristics. Now, I just mentioned in the last slide that the inner planets and the outer planets, or the terrestrial and the Jovian planets, have vastly different characteristics, and that has to be explainable using the solar nebular theory. And if it is explainable, then that just gives more confidence to the solar nebular theory. Now, the solar nebular theory is that, again, there's a cloud of gas and dust that from which formed the sun and the planets, with the sun at the center. And I know when we talked about the reason for seasons on Earth, I try to discourage you from thinking about what I call the campfire analogy, or the proximity. Some people think that it's hot in the summertime because the Earth is closer to the sun, and it's cold in the wintertime because we're farther away from the sun. And I try to discourage that kind of thinking because while there is some variation during the course of the year, it's very minor. And the real reason for the seasons, as you now know, is because of the Earth's tilt with respect to the orbital plane. That said, now we have to start thinking about proximity effect when we start comparing the planets, because the planets are at vastly different distances from the sun. And that's what we see here in this graph. We see the temperature listed on the y-axis. We see distance from the sun on the x-axis. And again, you should know your planets at this point, and you may actually already know the distances. Turns out that Mercury is about 0.4 AUs away from the sun. Venus is about 0.7. Earth is 1 AU. Mars is 1.5 AUs away. Jupiter is 5 AUs. Saturn about 10. Uranus about 20. Neptune about 30 AUs away. And one thing you'll notice on this graph is that as you get farther away from the sun, the temperature at that location is much colder, which again makes sense. When you're close to a campfire, it's warm. As you get farther and farther away from the campfire, it gets colder. Now, why is this important? Because in the early solar system, what we see here are some of the temperatures. In fact, I'm going to go ahead and slide. So as I slide, let's say when Mercury is forming, the temperature was around 1200 Kelvin. That's pretty hot. 1200 Kelvin is hot. In fact, so hot that the only stuff that would have been solid at that location would have been metals and metal oxides. Everything else would have been essentially gas in their gas form, because it would be so hot that close to the sun that those elements could exist, but they would exist in their gas form. They would be vaporized. And if you're going to build a planet, you need essentially solids to build from. You can't really build a planet effectively using gases. It's a lot easier to build using solids because you want things to smush together. So the building material that was available at Mercury's position in the early solar system would have been metals and metal oxides. Now, as we get farther away from the sun, we notice that it gets cooler, and that then gives you a greater range of building materials. Now, the stuff that is possibly solid at that location would be not only the metals, but also silicates, rocks, essentially, feldspars and such. And so therefore, Venus, Earth, Mars have not only silicates to work with, but metals and silicates to work with. Now, as we get farther out from the sun, it's much colder out at the location of Jupiter, Saturn, and such. Now, things like water are no longer, they're not vapor, they're actually liquid and gas form. I'm sorry, liquid and solid form. So you have water ice that's available. Ammonia ice, methane ice. Methane here on Earth is natural gas. Methane here on Earth at normal temperature and pressure is always going to be a gas, but farther away, where it's colder, the methane actually forms a solid, and so forth and so on. So now you have a different grouping of building materials from which to build your planets. So that's very important, and this the fact that this is consistent with the solar nebula hypothesis, again, helps us to understand why the different planets have different characteristics. And this is a neat little simulation that allows us to explore some of the properties of the different planets. I'm going to actually drop out Pluto because we're just going to not consider Pluto for the time being. We really just want to compare and contrast terrestrial planets versus Jovian planets. And the first property that we're exploring here is the distance. Well, obviously, the distance increases as you move along from Mercury to Neptune. No big surprise there. How about orbital period? What do we mean by orbital period? Remember, orbital period is essentially the length of the year. How long does it take the planet to orbit once around the sun? Well, clearly, as we learned in Kepler's third law, there is a mathematical relationship. It was that p squared equals d cubed thing. You know, what's the length of a year on Earth? It's 1 year. What's the length of a year on Venus? 0.62 years, 0.24 years, et cetera, et cetera, et cetera. What you realize is that the farther away a planet is, the longer its year is going to be. Okay, that's relatively straightforward. Let's check out the mass of the planets. And notice there is a distinction, or a good contrast here between your terrestrial planets, all less massive than your Jovian planets. Pretty clear there. How about number of satellites, meaning how many moons? Notice Mercury has no moons, Venus no moons, Earth one moon, Mars 2 moons. And again, those moons are, as we're going to find out, relatively minor. Phobos and Deimos. This is one of those things in a comparative planetology class, you'd have to actually memorize the names of the moons and some of their characteristics. For me, it's more important that you understand, well, gosh, the inner planets don't have many moons. That's one of their characteristics. The outer planets all have a lot of moons. And these numbers may actually not even be updated, but you can tell there's plenty more moons for the outer planets than there are the inner planets. Density. Now, we already talked about mass, but one thing you have to understand is that density is mass divided by volume. So even though we saw that the inner planets are not very massive, they are relatively massive for their size. And that's because of the stuff they're made of. Remember that the inner planets are formed where only metals and silicates could be used as building material. Well, metals and silicates are dense materials compared to ices. So therefore, the inner planets are all much, much more dense than the outer planets. In fact, Saturn has a density of about 0.7, which means that it is less dense than water. So Saturn would actually float in a bathtub if we had a bathtub big enough. So that's all pretty interesting. And again, that's all the fact that the outer planets all have small densities, despite the fact that they had large masses, has to do with the sizes. Notice the radius of the outer planets. They're just much bigger than the inner planets. So despite the fact they have larger mass, they also have much, much larger volumes. Remember, density is mass divided by volume. So even though the outer planets are more massive, they're much, much more voluminous, and therefore they wind up being less dense. Okay, so of the solar nebula, this cloud of gas and dust, the sun certainly formed from that material. The planets formed from that material, but there was still some leftover stuff. And that's what essentially became asteroids, comets, and meteoroids. We'll talk more about this in the coming slides. Okay, so we've discussed where asteroids, for the most part, are located between Mars and Jupiter. The comets, and again, we're going to talk more about this when we get to chapter 12. So next module, we're going to talk more about asteroids and comets. But suffice it to say that comets are made of ice, primarily, and their source region is actually beyond Neptune. So whereas the asteroids are for the most part between Mars and Jupiter, kind of within the solar system, comets actually come from farther out, farther away, beyond Neptune. In fact, there's an area called the Kuiper Belt beyond Neptune that some comets come from, and there's another area called the Oort cloud, which is much, 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 much farther away from the sun. But again, from those cold regions where essentially ice is the only building block from which things can be built, that's where comets are generally the source regions. Now, one thing you'll notice, and again, more to be covered when we get into chapter 12, but when comets get closer to the sun, and most of them are, they're part of the solar system in the sense they're gravitationally bound to the sun. They quite often have very elliptical orbits, and as their orbits carry them closer to the sun, only then do we actually start to see them, because only then is the ice vaporized into what's called a tail. And the tail always points away from the sun, because it turns out it's the radiation pressure, the solar wind of the sun, that is influencing the direction of the tail. But again, we'll talk more about those details as we get into chapter 12. Okay, if you made it this far and are still thinking about the solar nebula hypothesis or the solar nebula theory, you've seen there's a lot of evidence that supports the solar nebula theory. This idea there's a cloud of gas and dust that rotated and formed this disk from which the sun and the planets formed. Again, the motions of the planets, the sizes of the planets, some of their characteristics, all this is supporting evidence for the solar nebula hypothesis. But another part of the solar nebula hypothesis is that this all occurred about 5 billion years ago. Well, how the heck do we know? Best method that science currently has is what's called radioactive dating, where you can take elements, radioactive elements, and see how much of the byproducts of decay are in a material, and you can then figure out how long that material has been around. So a more common form that you may be familiar with is what's called carbon-14 dating, and that's used to measure the age of artifacts that are carbon, that contain carbon. So a skeleton, you can figure out how long ago that person lived by using carbon-14 dating. And again, that's pretty common, but that's only good for things that are about 50,000 years old. The half-life of carbon-14 is about 5,700 years, and therefore, after it's gone through several decay generations, there's so little of it left that you can't get enough to really sample. That's not true of other types of elements. So other elements are used to determine the age of older stuff, such as rocks, things that are not organic. And it turns out that rocks here on Earth, as well as rocks that have been found from the moon or from Mars, and again, these are typically asteroids that have wound up being meteorites here on Earth that we can tell come from Mars or come from the moon. They all essentially trace back to the same age, which is about, here on Earth, oldest rocks are about 4.4 billion years old. Rocks from Mars and the moon indicate an age of the solar system around 4.6 billion years. We've already compared some of the characteristics of the different planets. We've discovered that the inner planets are indeed more dense than the outer planets. They're relatively small masses, but also very small volumes. And it turns out that their observed density currently is a little different than their uncompressed density. That's when they first formed. And that's because over time, their own gravity has smushed them. And of course, the Earth, being the most massive of the inner planets, has essentially pulled inward on its own material. It's smushed the material of the Earth to make it more dense. So if you look at the uncompressed density column over here, you would see that at the time of formation of the solar system, Mercury was the most dense of the inner planets. And now if we compare, we see that the Earth just barely squeaks it out, being more dense than Mercury. And again, that's because of the fact that Earth is the most massive of the inner planets and therefore has a larger gravitational pull, and not only pulling on other stuff like the moon and such, but also pulling on itself, smushing itself. So therefore it's got the greatest observed density currently. Okay, so once you do have a cloud of gas and dust that's kind of spread out into a disk, and you have all this material to work with, the question is, how does that material kind of get together? And it's through several different stages. The first is condensation. The very smallest, atoms, molecules start to link together, and they form little bits of material. Those bits of material then can kind of glom onto each other. That's the process called accretion. And once you've glommed on enough, you actually have what are called planetesimals. And as those planetesimals then run into each other and collide, you get protoplanets, and then eventually you get full planets. Okay, so we've already seen how the solar nebula theory explains the observations of the different characteristics of the planets, but one thing we haven't really talked about is the interior structure of planets, because the solar nebula theory has to be able to explain that as well. And it turns out that we've been explaining how planets actually formed through this process of condensation and accretion, and then the formation of planetesimals, and eventually you get a planet. Another very important step is what's called differentiation. So you have all these planetesimals crashing into each other, sticking together, and forming essentially a very basic planet. And through all those collisions, the material does get heated up because of the friction and the bombardment that occurs in the formation of a protoplanet. So you have a fairly warm body. That warm body is also heated by radioactive decay. We've already talked about the fact that elements can decay into other isotopes or into other elements, and in the process they give off energy. So you actually have heating that occurs not only because of the collisions and the friction, but also because of the radioactive decay of the materials themselves. So you have a planet that gets warm to the point that it becomes molten. So all these solid materials that form the planet now become molten. They become liquid through both the heating of collision, compressional heating of gravity, as well as radioactive heating. And once you have a molten material, now you can have what's called differentiation. Differentiation is when you have different materials of different densities. The dense stuff is going to sink to the center, and the less dense stuff is going to move toward the surface. And that's what happens. You wind up with a resulting planet that has the dense stuff in the middle at its core, and the less dense stuff out on the outside. That's called the crust. Okay, so up till now we've been talking about the evidence from within our own solar system that supports the solar nebular theory. Now, and within recent decades, we've been able to look outside our own solar system at the formation of other solar systems and get supporting evidence. The fact that we're seeing similar characteristics occurring in other newly formed solar systems gives more evidence to, or more confidence in the solar nebular hypothesis. One problem is that for extrasolar planets, it's tough to see them directly. You can't just see an individual planet around another star, because first of all, the star is far, far, far away. Even our next nearest neighbor, apart from our own sun, is Proxima Centauri, which is like 4.3 light years away. So at that distance, even the star itself is very, very small. And then you're trying to pick out planets, and remember that planets don't produce their own light, and so you can see the star because it's producing its own light. It's really difficult to see the planets because they don't produce their own light, and the planets are much, 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 much smaller than the star itself. So therefore, you have to find other techniques with which to detect extrasolar planets, also known as exoplanets. So how can you tell if there's a planet going around a star? Well, all planets have mass. And as we've discussed, all things that have mass have gravitational pull. And so the sun pulls on the Earth, clearly. That's what keeps the Earth in orbit around the sun. But the Earth also pulls on the sun and creates a certain amount of wobble to the sun. Similarly, if we're looking at other stars, if they've got planets around them, those planets should be producing a certain amount of wobble in the star. And therefore, that's going to create some radial motion of the star with respect to the Earth. It's going to either be moving away or toward the Earth, and therefore we should be able to pick up a Doppler shift in that star's spectrum, if indeed it's being tugged on by one or more planets. Such as in this case, they show an example of a dog pulling on a person, or several dogs pulling on a person. And that would of course add to the complexity of the wobbling. We're going to see in the next slide an example with a hammer thrower. Okay, so much like a planet orbits a star, and of course the planet remains in orbit only because the star is exerting a force on the planet because otherwise it should move off in a straight line out into space. But from Newton's first law, we know that the planet does indeed stay, it changes its direction. The only reason is because there's a force of the planet, of the star acting on the planet. In a similar way, and from Newton's third law, the planet must exert a force on the star, and it's going to be an equal amount of force, just in opposite direction, and therefore it causes the star to wobble, just like we see this hammer thrower. Okay, so here's a simulation that allows us to show the influence of planets on a star, in our case, our sun. And so let's choose a planet. Let's choose our Earth and see what kind of an effect we have on the sun's wobble. Not very significant. I can't see very much of a wobble. Let's choose something a little more massive, such as Jupiter. Notice what happens when we throw Jupiter in here. Notice this is the amount of wobble that just Jupiter has on the sun. You can see how much wobble Mercury produces. It's closer to the sun, but it's also much less massive, so not a huge effect. What if we just have Saturn thrown in there? Saturn produces a certain amount of wobble, but not as much as Jupiter, probably because Saturn is less massive, and also because Saturn is farther away. Okay, so you'll face this a similar simulation to this in the lab activity you're going to do for this module, which has to do with, again, exoplanets. And so here we have a star being orbited by a planet, and we see the amount of wobble that is being produced on this star. Again, the crosshair here indicates the center of mass between these two objects. And so the planet is orbiting the star. The star is orbiting, they're both actually orbiting their common center of mass. And again, that's going to be explained when you get to the lab activity. But what I want you to notice is that the observer is looking at the star, and the star appears to be moving toward the observer. Right now, in fact, moving toward the observer, toward the observer, toward the observer. And now the star appears to be moving away from the observer. And that's what astronomers look for. They look for red shifts and blue shifts in the star's spectrum to indicate times when it's moving toward the Earth and times when it's moving away from the Earth. It turns out that when the star is moving toward the Earth, you wind up recording that as a negative radial velocity. And when the star is moving away from the Earth, it winds up being a positive radial velocity. So that hopefully will help you when you get to the beginning part of the student guide that makes up this module's lab activity. Okay, just to make it a little more clear as to how this radial velocity technique is used in detecting exoplanets. Here we have a star, and that's the yellow dot. We have a exoplanet. That's the gray dot, and we're viewing this star using a telescope, and we're seeing the absorption spectrum produced by that star. We're seeing, that's what we have down here, all these colors. Remember, those dark bands are just elements that make up the star's atmosphere, so we could figure out the composition of the star. That's about all we can figure out just by using just the raw spectrum there, the absorption spectrum. Now I'm going to set the animation into motion, and we'll see what happens. So notice the black lines there are moving, right? They're moving to the right. They're moving to the left. And so when they move to the right, we would call that a red shift. When they move to the left, we call that a blue shift. And again, that is indicative of the radial velocity of the star. The star is moving, when the star is moving away from the telescope or from the observer, you have a red shift. The absorption lines tend to move toward longer wavelengths. As those absorption lines move toward shorter wavelengths, that means the star is moving toward you, and we call that a blue shift. Okay, so now we've moved into chapter 9, and actually chapters 9 and 10 have kind of combined in the rest of the remainder of this module here, because this essentially deals with the terrestrial planets. And so what you see here is images of all the terrestrial planets, Mercury, Venus, Earth, and Mars, as well as, of course, the Earth's moon, thrown in there for good measure. Just to give you an idea of the relative sizes, notice that Venus and Earth are almost the same size, Mercury and Mars being much smaller. The little text blocks have some of the interesting characteristics of some of these different planets. The next slide that you're going to be looking at actually is a song that I wrote years ago, which actually deals with all of the planets. So for this module, we're just going to be focusing on the terrestrial planets, but this song that I wrote actually will teach you not only the planets in order from sun outward, but also some of the important characteristics of each planet, and it's called My Very Educated Mother. I hope you enjoy. My mom, I'd wager, was an English major. She knows her ABCs. She's got a BA, an MA, and PhD from a place called MIT. So it has helped that I am needing with my spelling and my reading. She says, it's no bother. But when I took it for granted that she'd help me with my planets, she said, go ask your father. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. So I came up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. Planet Mercury's closest to the sun, and I tell you, it's a hot little number. A year lasts about a day, and the sun's strong rays can leave you with a pretty bad sunburn. For what it's worth, from Mercury to Earth, just one planet stands between us. Endowed with a shroud of poison gas clouds, the lovely planet Venus. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. I tried to come up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. The fourth rock from the sun is thought by some to be the most similar to ours. The pole's made of ice, it's about half the size of the red planet known as Mars. And a blast from the past made a giant mass of gas. I couldn't write a rhyme much stupider. It looks like a dot, it's got a giant red spot, and we call it the planet Jupiter. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. I tried to come up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. When we reached planet 6, it all started to click, and Mom was picking up the pattern. Who wins the pretty planet prize? It's safe for sore eyes, the ring beauty known as Saturn. And it's me and you, the last two are blue, with atmospheres that could not sustain us. In fact, they're practically twins except for how the one spins, and now you know your Neptune from Uranus. I was shocked when I discovered that my educated mother could not name the planets. I tried and tried to help her memorize, but she just can't understand it. I tried to come up with a system that might help her list them. At least that's how I planned it. Cause I was shocked when I discovered that my educated mother could not name the planets. I was shocked when I discovered that my educated mother could not name the planets. Now, several slides ago, we talked about differentiation, which explains the interior structure of planets. Well, how the heck do we know about the interior structure of planets? We just talked about this when we talked about the sun back in module, what was it? Module 7. I'm sorry, Module 6, Chapter 7. And we use seismology techniques to learn about the structure of the interior of the sun. Same thing with the Earth. The Earth, actually, we know very little about as far as direct exploration. We've barely scratched the surface. It's tough to drill into the Earth, but you can figure out a lot about the Earth's interior just by using seismic waves, either earthquakes or man-made seismic waves. You can determine the general structure and different layers of the Earth's interior. Okay, so plate tectonics is essentially the idea that the Earth's crust is made up of essentially plates, and those plates are able to move, and that's why the Earth's surface has changed over time. Not only the orientation of the continents, but the fact that we have new crust that's always being created. We have old crust that's always being destroyed. We wind up with volcanoes and mountain building, all that kind of stuff. That's all due to what's called plate tectonics. Plate tectonics is only observed on the Earth. It's not a feature of any of the other terrestrial planets. One thing that I hope you like about the Earth is the fact that it's got a life-sustaining atmosphere. What's the Earth's atmosphere made of? Well, primarily nitrogen, actually. When you take a good deep breath, 78% of what you're breathing in is nitrogen. 21% of what you're breathing in is oxygen. So therefore, 99% of everything you take in is either nitrogen or oxygen. The remainder being argon, carbon dioxide, etc., etc. The Earth's atmosphere has not always been life-sustaining. It's not always been that same composition. It has changed over time. We started out with essentially a primeval atmosphere of just captured gases. The balance or the mixture changed over time through outgassing, the fact that trapped gases from the interior of the Earth were released via volcanoes. We also had bombardment, the fact that we were being clobbered by stuff. Helped to bring in new material, including water, because it turns out that the amount of water we have here on Earth cannot be explained if you go back and use the solar nebula theory and figure out the composition of what the early Earth would have been. There wouldn't have been enough water to account for the current amount of water. So where did the water come from? It came from the fact that we're constantly being bombarded by these icy balls called comets. And of course, we have continued to change the composition of the Earth's atmosphere by natural reasons as well as by man-made reasons, which we'll talk about here in a second. Now, why is life possible here on Earth? Well, partly because we have liquid water on the surface of the Earth. Another reason is because we have a life-sustaining atmosphere. Another reason is the greenhouse effect. The greenhouse effect sometimes gets a bad rap, but the greenhouse effect actually makes life possible. If it weren't for the greenhouse effect, it would be much colder here on the surface of the Earth than it actually is. And let's kind of explain why. Now, what is the greenhouse effect? The reason why it's called the greenhouse effect is that the Earth's atmosphere acts in a similar way. It's not completely analogous, but we use the idea of a greenhouse to symbolize the Earth's atmosphere. Because what happens is, of course, the Earth, so the sun, produces a lot of visible light. It produces, as we've discussed way back in chapter 6, the sun produces all kinds of light, but it produces a lot of visible light. So it has this visible light coming into the system. In this case, coming into the greenhouse through the windows, right? And we know that glass is essentially transparent to visible light. Well, why is that? Because you can look out the window and see your car out in the parking lot. Right? If the glass was not transparent to visible light, you wouldn't see anything outside. So we know that visible light can easily pass through the glass of a greenhouse. It then hits the plants and it hits the benches and the floor and all that kind of stuff, and it warms that stuff, right? In fact, well, the visible light, some of the visible light is reflected. That's why we can see a plant, for example. A lot of the light is reflected, but some is absorbed. And that energy that's absorbed helps to warm the plant. Now, the plant does not get so warm that it emits visible light. It would have to be so hot that it's glowing or essentially burning up. That's not what happens, but it does warm up some. And because it is a warm body, it's a black body, it's going to produce energy. It's going to emit energy on its own. It's not visible light. In this case, it's infrared. That's what these longer wavelengths are indicating. So the plant there, the pot, is emitting infrared radiation, but that infrared is not allowed, it's not able to pass through the glass. The glass is not transparent to infrared, so the infrared then gets reflected within the greenhouse. So therefore we have an input of energy in the form of sunlight, and yet the energy is not able to escape, and that's why the temperature inside the greenhouse increases. So you have a net addition of energy, which is reflected in an increase in temperature. Same thing happens here on the surface of the Earth. Certainly we have the light from the Earth, light from the sun that hits the surface of the Earth, and part of it is reflected, but some is absorbed that heats the Earth. That the Earth then is not glowing hot, but it is warmer, and therefore it emits infrared radiation. But unlike the atmosphere is transparent for the most part to visible light. We talked about that as far as the transparency of the atmosphere to certain wavelengths of light. The atmosphere is primarily transparent to visible light. It is not transparent, if you remember, to infrared radiation. So that radiation gets absorbed by the atmosphere, and some of it gets re-emitted down to the surface of the Earth. So in addition to having a source of energy from the sun, we also have a source of energy from the Earth's atmosphere. That keeps us a little bit warmer than we otherwise would be. So that's a good thing. The greenhouse effect is a good thing, except when you start getting too many greenhouse gases in the atmosphere, and that's what's going on right now. For a long time, we've had this amount of carbon dioxide in the atmosphere. And within the last 150 years, essentially from the beginning of the Industrial Revolution, we see this very, very dramatic spike in the amount of carbon dioxide in the atmosphere. And carbon dioxide is indeed an infrared emitting greenhouse gas. So where did this come from? Is it natural? Is it not natural? It is definitely not natural. It is the fact that we have taken fossil fuels. Fossil fuels are just essentially solid forms of carbon. They're called hydrocarbons. So over millions of years, plants gobbled up carbon dioxide out of the atmosphere and through photosynthesis stored that carbon away in the form of hydrocarbons and cellulose and all kinds of material that made up the structure of the plant. Those plants got buried over time. So essentially we sequestered, we locked away all this carbon over the course of millions of years. The plants removed carbon from the atmosphere and stored it away in fossil fuels that got buried deep in the earth. All of a sudden we started to mine them and burn them and liberate the carbon dioxide. In the process of combustion, when you burn something, you take oxygen, and in the presence of energy, like a match, you burn the material and you liberate carbon dioxide. So we are now taking carbon, which it took millions of years to store it away, and now we are liberating it in a matter of 150 to 200 years. And that's why we see this dramatic change in the composition of the atmosphere. And that's the real danger. That's why global warming is a major topic that's going to affect your life, is because we have altered the Earth's atmosphere by virtue of burning fossil fuels at a tremendous rate. Since we're talking about the terrestrial planets, and of course the Earth and the Moon are part of the terrestrial planets, I wanted to step through a little activity that I always do with my students, which is a way of helping them to appreciate not only the relative sizes of the Earth and the Moon, but also their distance from each other. So one thing I always ask is, how big is the Earth? Well, you should know, perhaps we've run into it a couple times. The Earth is about 8,000 miles in diameter. How about the Moon? The Moon is about 1/4 the size of the Earth. So if we do a ratio of their sizes, you wind up with about a 4-to-1 ratio. So let's let a basketball be Earth. And so if the Earth is a basketball, then a tennis ball would be about 1/4 the size of the Earth. So the question is, how big would you, or how far away, if that's our scale, that the Earth is a basketball and the Moon is a tennis ball, where should the tennis ball be located with respect to the Earth in order to indicate the proper distance, the proper separation between Earth and Moon? So think about that for a second. Where would you put it? And then I'll explain about how we actually go about figuring that out. So let's let the Earth, let's actually work some numbers here. The actual distance from the Earth to the Moon is about 250,000 miles, 240,000 miles. What's the Earth's circumference? About 24,000 miles. We did that, remember back for that Eric Idle song. We just took pi times the diameter. We know the diameter is 8,000. 8,000 times 3, or pi, is 24,000. So we get a circumference of 24,000. So what's the ratio there? What's the ratio of the distance between the Earth and the Moon and the distance around the Earth one time? It's about 10-to-1. So can you imagine we take a string and we wrap the basketball. Remember, the basketball is the Earth. If we wrap it with a string, we're essentially figuring out the circumference. So we know that the separation between the Earth and the Moon has to be 10 times greater than the distance around the Earth one time. So let's wrap our basketball 10 times, then unwrap that string and see how far that takes us. And it turns out that if you actually did this, it would be about 30 feet or so. Would be how far apart the Moon would have to be from the Earth. The Moon tennis ball would have to be away from the Earth basketball in order to properly represent the Earth-Moon distance at this scale. And you can figure it out for yourself. Once you've done this, and I encourage you to do this with a partner, figure this out, and then stand at that proper distance with one of you holding the basketball, one of you holding the tennis ball, and ask yourself, is that proper? Does that properly show the separation? And one way of checking that out is the person who's holding the basketball should extend their arm and hold up a pinky and try to cover the tennis ball with the pinky. Because it turns out that your outstretched arm, the width of your pinky is about 1 degree. So you can actually, if you started from your horizon and started stacking your pinkies, you should be able to go about 90 times to go straight overhead to your zenith, or 180 times from your southern horizon to your northern horizon. So if you recall, when we talked about eclipses, the moon's angular diameter is only 1/2 degree. So if your pinky is at 1 degree and the moon is only supposed to be 1/2 degree, then your pinky should easily cover the moon. So I encourage you to try it out. Now, if we use the same scale and we wanted to get the sun involved, if our basketball is Earth, the sun would have to be 82 feet in diameter. We would need to have an 82-foot diameter ball to represent the sun at this scale. And I show a baseball field here only just to show that the distance from from home plate to first is 90 feet. So you would need a big old sphere whose diameter would be essentially the distance from the home plate to first base. That would be your sun. And those are tough to come by. So remember, our basketball is our Earth. This huge 82-foot diameter thing would have to be our sun. So how far, if we had such a large ball, how far would we have to put that ball from us to properly represent the distance from the Earth to the sun? We play the same game. We take the Earth-Sun distance, and we divide by the circumference of the Earth, and you wind up with this ratio, which means we need to wrap our Earth basketball 3,720 times with a piece of string, and then unravel it, and that's how far away we would have to start walking to place our sun. And that winds up being about 1.5 miles. Well, we can't do that. That's too big for classrooms. So what I do is when I do this in my traditional class, I shrink this. I make the sun an 18-inch exercise ball. Let's pretend that's our sun. And then we do the same thing. We scale it. So if I divide the actual diameter of the sun by the diameter of my exercise ball, that allows me to set up a little scale system. And it turns out that 1 inch of my exercise ball is about 50,000 miles, which means in this new scale, this new system, my Earth, instead of being a basketball, would only be a ball that would be a fraction of an inch. And of course, the moon, being even 1/4 the size of the Earth, would be even smaller still. At this same scale, with those tiny little balls being Earth and moon, they'd only have to be 5 inches apart from each other. The Earth-Sun distance, if I did the numbers, would have to be 162 feet. So I'd have to take my exercise ball and walk 162 feet in order to place it at the proper distance so that it properly represents the distance from the sun to the Earth on this scale. And again, once I do that, I always have my students also check it again. Because remember, the sun's angular diameter just so happens to be 1/2 degree. And so therefore, their outstretched pinky should also easily cover the exercise ball if somebody walks away 162 feet from the person who's pretending to be the Earth. And of course, if you think about that, that means you've got a 162-foot circle with an exercise ball at the center, and the Earth is this outer, you're out here somewhere, and then what else is in between you? Just Venus and Mercury. Those are the only two objects that are in between the Earth and the Sun. And of course, those are just specks, right? Only about 0.16 or whatever, less than an inch in diameter, and the rest is actually empty space. That's pretty cool. Okay, so one thing you'll notice on this image, and this is an image I believe out of the book, is that the moon's surface actually has some variation to it. It's got some dark areas, it's got some bright areas, it's got some mountainous areas, it's got some flat areas. These are actually named different things, highlands and lowlands, or the lowlands are actually usually called Maria, or it's Mare is the singular version. It means sea, I believe, in Latin. And what we learned about this, and they all have names, and even each crater actually has names, but we don't need to know all that stuff. What we do need to know is that the cratering actually will indicate the age of that part of the lunar crust, because even though the moon appears to be cold and dead now, it's not always been that way. At one point it had magma just barely under the surface, and so when the moon was getting clobbered by asteroids early in the formation of the solar system, shortly after the moon actually formed, it could resurface itself, just like the Earth resurfaces itself even today. If we were to get smacked by something in 1 million years, 2 million years, that crater may go away because of either weathering or through plate tectonics. When the moon had magma close to its surface, when we get smacked by something, the magma would then spread out onto the surface and resurface part of the moon's surface. And so the number of craters is somewhat indicative of how old your crust is. An area of the crust that has fewer craters means that it must be a fairly new portion of the crust, and therefore it reformed, it resurfaced itself, and there haven't been that many impacts since that resurfacing occurred. If you have an area of the moon where there's a lot of crater marks, a lot of blemishes, that's going to indicate that's part of the moon's surface that has not been resurfaced any time in the recent past. Okay, and this graph just indicates the fact that early on in the solar system's history, when a lot of the planets were first forming and when the solar nebula still had not been cleared, there was a lot of stuff out there with which to be bombarded by. And the amount of bombardment has decreased over time because there's less and less stuff available to do the bombarding. Okay, so how are Maria formed? Again, this is sometimes, the analogy is quite often given of a creme brulee. If you're familiar with that dessert, you may have to do a little internet search on it. A creme brulee is essentially a dessert that's got kind of a custard with a hard caramel surface on the top, and you essentially crack the hard caramel surface in order to get to the good stuff below. Same thing happens in the formation of Maria. The fact that you've got magma under the surface, but a large impact will actually crack the crust and allow magma to flow onto the surface, and that, of course, when that occurs, then it becomes lava and it cools and it essentially resurfaces the moon. That's how Maria are formed. Okay, so within our chapter, our module now, where we're really dealing with the solar nebular theory, there's also another theory, and that has to do with the formation of the moon. How did the moon form? And in the past, as your book describes on page 180, there were a couple of different hypotheses: the fission hypothesis, the condensation hypothesis, the capture hypothesis. The leading hypothesis currently is what's called the large impact hypothesis, the idea that shortly after the Earth started to get its act together and formed as a protoplanet, it got smacked into by another large protoplanet, almost the size perhaps of Mars. And essentially the two centers of those protoplanets combined and formed one large planet, which is the Earth, and then left a bunch of debris as almost like a ring. And that the ring then accreted over time and formed the moon. And there's, again, a good hypothesis always has evidence. It's not just a guess. There's got to be evidence. And part of the evidence that supports this hypothesis is the fact that the Earth and the moon have different chemical compositions. The Earth is much more dense than the moon is. The Earth has a lot more iron than the moon is. And that's partly because the Earth, at the time of this collision, was already differentiated. Its dense stuff, like iron and nickel, was already at the center. Likewise, this protoplanet that we smacked into us, also had differentiated. And it turns out that the centers, those two iron centers, essentially combined and left the Earth much more dense than the moon. The moon formed out of material that was a much lower density. And so therefore, it's a piece of evidence that supports the large impact hypothesis. Okay, so I'm not going to go into great depth as far as knowing a lot of facts about Mercury. As I mentioned in my song, Mercury is a hot little number. A year lasts about a day, and the sun's strong rays can leave you with a pretty bad sunburn. Planet Mercury is the smallest and the closest to the sun. It does not have much in the way of an atmosphere, and it has a lot of craters. So actually, the surface looks very much like the moon's surface. Okay, again, a year lasts about a day. Remember that a day is the amount of time it takes for a planet to rotate once on its axis. A year is how long it takes the planet to go around the sun. And it turns out that the planet Mercury is almost tidally locked to the sun. It's so close that it's almost tidally locked, much like the moon is tidally locked to the Earth, in the sense that we only see one side of the moon. The orbital period of the moon is the same as its rotational period. It rotates once on its axis once a month. Same thing with the amount of time it takes to orbit around the Earth. So with Mercury, Mercury takes about it's the time that it takes to go around the sun one time is about 1.5 times the time it takes for it to rotate once on its axis. So that's why I say a year lasts about a day. So a day on Mercury is 59 days, and a year on Mercury is 88 days. So they're about the same. So that means that the side that faces the sun for a long time. And that's why you can get a pretty bad sunburn. In fact, it gets very, very hot. For the sun-facing side, notice that the temperature, 600 Kelvin, is your daytime temperature. But if you're the problem with Mercury, which is a little different than Earth, is that despite the fact that it's very close to the sun, it can get really cold. Notice 100 Kelvin, which is a negative 173 Celsius, is the temperature on the nighttime side, despite the fact that you're close to the sun. The reason being is you're close to the sun, but you're facing away from the sun. And unlike the Earth, which has an atmosphere from which we can get energy, if you're facing away from the sun, even if you're on Mercury and close to the sun, you're getting nothing. You're only getting energy if you're facing toward the sun. If you're facing away from the sun, you are truly left out in the cold. There's no atmosphere to provide energy, and that night lasts a long time. Part of the reason why we don't have a huge temperature contrast from day to night here on Earth is A, because we have an atmosphere, and B, because we rotate relatively quickly. It only takes us, we're only in darkness for a maximum of 12 hours before we start seeing sunshine again. Okay, so when we talked about the evidence for the solar nebula hypothesis, one of the key parts of key pieces of evidence was the fact that all planets orbit counterclockwise, and the majority of planets rotate counterclockwise. You would expect all planets should rotate counterclockwise. It turns out that most of them do, with the exceptions of Venus, Uranus, and Pluto. The exact reason as to why Venus rotates clockwise, despite the fact that it orbits counterclockwise, is not actually known. But there is a possibility that it may have, somewhere along the line, really gotten clobbered by something which caused its rotation to change and to rotate clockwise versus counterclockwise. Okay, so here's the breakdown as far as the composition of the Venusian atmosphere. Again, mostly carbon dioxide, and then other kind of nasty stuff, hydrochloric acid, hydrofluoric acid. And you can see that the runaway greenhouse effect does indeed lead to a surface temperature that is above 700 Kelvin, compared to the profile, in the dashed line here is the profile of the Earth's atmosphere, where our surface temperature is around 273 Kelvin. Okay, if you recall the song, the fourth rock from the sun is thought by some to be the most similar to ours. With poles made of ice, it's about half the size, the red planet known as Mars. So Mars is indeed about half the Earth's diameter. So it's got some dissimilarities and some similarities. It doesn't have much in the way of an atmosphere, but the atmosphere that it does have is mostly carbon dioxide. It does have some winds and dust storms and that sort of stuff. It does not have tectonic activity. It does have a tilt to its axis that's similar to the Earth's, and therefore Mars does indeed experience seasons, just like we do. And its length of day is also similar. It rotates once upon its axis every 24 hours. However, its length of year is obviously going to be longer than Earth's because it is farther away from the sun than the Earth. Okay, this is a slide that we're actually going to expand upon a little bit more in the next module, but just wanted to briefly introduce it to you. The fact that different planets can hold on to different types of atmosphere and can hold on to different densities of atmosphere depending upon, first of all, the temperature of the planet and its mass. So, a more massive planet has a greater gravitational pull and should be able to hold on to gases more easily. But that's not the only factor. It also depends upon where that planet is located. If it's closer to the sun, the gases are going to be hotter and therefore going to have more energy. They're going to be zipping around faster, tougher to retain compared to if you're farther away from the sun. In a colder location, those gases are going to be moving around slower and therefore will be easier to capture and retain. So there's a lot of factors that go into whether a planet can retain an atmosphere. For Mars, as you notice, it's pretty close to certainly it can retain carbon dioxide, because carbon dioxide at the location of Mars has a radial velocity, or a velocity, which is listed here on the y-axis, that is lower than the escape velocity of Mars at that location, which is around 5 kilometers per second. So it certainly can retain carbon dioxide. Nitrogen and oxygen, yeah, sort of. It can retain water. In fact, there is some water in the Martian atmosphere, mostly locked up as solid water in the poles. But it wouldn't be able to hold on to things like helium or hydrogen because those things are moving around too fast to be retained. Mars is home to the largest volcano in the solar system. It's called Olympus Mons, and it easily dwarfs any volcano on Earth. And part of the reason is because volcanoes on Mars form as what are called shield volcanoes. And that's because the plates, the fact that the Mars crust is not broken up into plates and they don't move around. And therefore, the crust just sits over a hot spot in the mantle and just grows and grows and grows as a volcano. On the Earth, you have volcanoes that are the result of what's called subduction, where one plate goes under another, and you also have some shield volcanoes, such as the Hawaiian Islands, but those occur as crust moves over a hot spot in the mantle, but the crust is constantly moving, and therefore it'll grow for a while, but then as the volcano moves off of the hot spot, it no longer grows, and it eventually will erode and go back into the sea in the case of Hawaii. So it just can't sit there and grow and grow and grow the way Olympus Mons has been able to do. Okay, so Mars has been the target of the most extensive exploration outside of our own moon by Earthlings, and that's because of the hope that there could perhaps be some liquid water on Mars and perhaps even the possibility of life, or at least former life, on Mars. There is evidence, in fact, there's proof now that there has been liquid water on Mars. There's many different lines of evidence for this. There's channeling on the surface. There actually is solid water found in the ice caps of Mars. Even though primarily the ice caps are dry, or sorry, are carbon dioxide ice or dry ice. But there is water ice as well locked up in the ice caps. There's also minerals that are only found in the presence of water here on Earth, and the same minerals are found on Mars. So that's also indicative of the presence of water, at least in the past, in parts of the Martian surface. So since there was a lot of water in the past, and even some locked up water in the form of ice in the present, there is still some thought that there is the potential for either present life or at least past life on Mars. So one of the characteristics that you may have noticed about the terrestrial planets is the fact that terrestrial planets do not have much in the way of satellite systems. In fact, for the terrestrial planets, the only two that have any kind of moons are Earth and Mars. The planet Mercury has no moons, Venus has no moons, Earth has one moon, and Mars has two moons, Phobos and Deimos, which are perhaps just captured asteroids from the asteroid belt, because Mars being very close to the asteroid belt, that may be where those came from. They're relatively small. In fact, they're so small they don't have enough gravitational pull to actually create complete spheres of themselves. So they're relatively insignificant moons. But moons nonetheless.